Rounding numbers is a useful skill. One example of useful rounding that you probably already do involves prices of items at a store. We often round prices such as 4.99 to 5. Numbers can be easier to discuss in conversation when they are rounded numbers. For example, 1,526.25 is a mouthful to say and hard to process. About 1,500 is much easier to say and easier to understand. Unless absolute precision is necessary, it's easier for both parties in a conversation to use 1,500 as opposed to 1,526.25. Rounded numbers are also easier to work with when doing computations, especially for mental computations. 1,526.25 plus 1,380.54 would be challenging to compute mentally. 1,500 plus 1,400 is much easier. 1,526.25 plus 1,380.54 is 2,906.79. 1,500 plus 1,400 is 2,900, which is pretty close to the exact answer. Again, if precision isn't necessary, then the computation with the rounded numbers is close enough to the right answer. The answer is 95% as good with only 5% of the work. In real-life situations, you will get to decide how much to round a number. For example, I decided to round 1,526.25 to 1,500. I rounded to the hundreds place value. However, I could have rounded it to the thousands place value, which would have yielded a result of 2,000. This is an even easier number to work with, but we lose a lot of precision. 1,500 is much closer to the original number than 2,000 is. That will always be the trade-off. The more rounded the number is, the easier it is to work with and discuss, but the less precise it is. In the examples that follow, we will not get to choose what place value to round to. The directions will tell us that. In order to get the correct answer, we must know the names of the place values in our numbering system. The following image labels the first several place values both before and after the decimal point. Take a minute to familiarize yourself with the names of these place values. Let's look at a few examples of rounding. Let's round 7,476,242,056 to the nearest 100,000. This is the closest number that is a multiple of 100,000. First, we must identify the digit that is in the 100,000s place. It is the 2 here. We will then have to make a decision. We will either keep this number the same, as a 2, or round it up to the next highest digit, a 3. To determine the correct decision, we look at the place value just to the right of the one we are rounding. For this example, that means looking at the 10,000s place, here. If this digit is a 4 or less, we keep the 100,000s place as a 2. If this digit is 5 or higher, we round it up to 3. Since the 10,000s place is a 4, we will keep the 100,000s place as a 2. Then, every place value to the right of the 100,000s place becomes a 0. The final answer is 7,476,200,000. This is considered rounding down, since the final result is less than the original number. Let's try rounding this same number to the 10 millions place. We will look at the digit just to the right. It is a 6. This means we will round the 10 millions digit up to an 8. All the numbers to the right of 8 become zeros. Our final answer is 7,480,000,000. This is considered rounding up, since the final result is more than the original number. We may also be asked to round numbers to place values that are located to the right of the decimal point. Let's consider this example. Round 3.141592 to the nearest hundredth. The hundredths place is located here. The digit to the right of this place value is here, which is a 1. Since this is 4 or less, we will keep the hundredths place the same, as a 4. All the place values to the right become zeros, so we get 3.140000. However, with decimal numbers, these trailing zeros can be dropped to get the number 3.14. 3.14 is the same as 3.140000. So our final result is 3.14. You might recognize this number as the number pi. 3.14 is a very common approximation of pi. Even 3.141592 is an approximation of pi. Pi extends to an infinite number of decimal places, though even NASA only uses pi to the first 15 decimal places in their calculations. Let's round pi to the 10,000ths place. In the 10,000ths place, we have 5. The digit to the right is 9, therefore we will round the 5 up to a 6. All the digits to the right become zeros, which we can drop. The final result is 3.1416. One last example. Let's round the number 7,984 to the nearest hundred. The digit in the hundreds place is a 9. The digit to the right of 9 is an 8. Since 8 is 5 or more, we will round the 9th up. The problem, however, is that there is no digit higher than 9. What happens in this case is that the 9 rolls over to a 0, much like the odometer on a car. Essentially, the 9 becomes a 10. The 0 stays in the hundreds place, but the 1 is moved to the next place value to the left. In this example, that would be the thousands place. It is carried over to the thousands place and is added to the digit already there. 7 plus 1 is 8. As usual, all the digits to the right become zeros, so we end up with 8,000 as our final result. Estimation is useful in situations where we want to simplify the mathematical calculations when we don't need a perfectly exact answer. We use estimation when we may just want to get a general idea of the answer, get somewhere in the neighborhood of the answer, and we want to make the math as easy as possible to get that approximate answer. Consider the following situation. A raise of $310,000 is evenly distributed among 196 professors. How much of a raise will each professor receive? The correct mathematical operation to find the answer is to divide $310,000 by the 196 professors to determine the amount of money each professor will receive. This is not a difficult problem to do with a calculator, but is a challenging calculation to do mentally. Rather than take the time to use our phone's calculator app to determine the answer, we can get a quick idea of the approximate amount of money each professor will receive by rounding the numbers to make the calculation easier. We will round to the highest place value for this problem. 310,000 rounds to 300,000 and 196 rounds to 200. Now, following the same reasoning as was previously outlined, we will take the approximately $300,000 divided by the nearly 200 professors. This is a much easier mental calculation. 30 divided by 2 is 15. The 2 zeros here will cancel out with 2 of the zeros here, leaving us with 2 zeros to follow the 15. Thus, the result is that each professor will get about $1,500. This is fairly close to the exact answer of $1,581.63 per professor. Let's consider another example. A full-time employee who works 40 hours per week earns $19.50 per hour. Estimate that person's annual income. First, let's determine the proper calculations. Then we will round to make those calculations easier to do mentally. Annual income means the amount of money earned for the entire year. If someone earns $19.50 per hour and works 40 hours in 1 week, then we can find their weekly income by multiplying 19.50 times 40. This would give us the weekly income. To find the annual income, we would need to know that there are 52 weeks in a year, a fact not given in the problem. We need to take the weekly income and multiply it by 52 weeks in a year to get the annual income. So, our answer can be found by taking 19.50 times 40 times 52. Again, this is not tough to do on a calculator, but challenging to work out mentally. We can make it easier on ourselves by rounding to estimate the annual income. Let's round 19.50 to 20. We can also round 52 down to 50. Then we will carry out the calculations on these rounded numbers to get an estimate for the person's annual income. 20 times 40 is easy to determine. 2 times 4 is 8. Then we take the 2 zeros here and place them behind the 8 to get 800. This person makes about $800 a week. Next, we multiply this result by 50. Using the same technique, 8 times 5 is 40. Then we take the 3 zeros here and place them behind the 40 to get 40,000. This employee makes about $40,000 per year. An important skill to develop is the ability to read information from a graph or visual representation of data. Consider the following bar graph. The first thing everyone should look at is the labels on the X and Y axis. In this graph, the X-axis is labeled as birth year, and the Y-axis is labeled as life expectancy. Thus, we have years along the X-axis and number of years of life along the Y-axis. By looking at the labels for the axes first, we have an idea of what information can be extracted from the graph. We are going to see a relationship between year of birth, 1950 for example, and how long a person could expect to live on average, 65.6 years for example. Notice that for each birth year there are 2 bars. We see yet another label here which tells us that the red bars represent male life expectancy, and the yellow bars represent female life expectancy. Thus, we can read from the graph that males born in 1950 have a life expectancy of 65.6 years, and females born in 1950 have a life expectancy of 71.1 years. Let's answer some questions using this graph. Estimate a man's increased life expectancy, rounded to the nearest hundredth of a year, for each subsequent birth year. To do this, we will look at the life expectancy of men in 1950 and compare it with the life expectancy of men in 2020. We specifically want to know how much it has changed in that span of time. The simplest way to measure change is simply subtracting the old value from the new value. In this case, to find how much men's life expectancy has changed, we subtract 77.1 minus 65.6. We find that men's life expectancy has changed by 11.5 years. Since this number is positive, we can conclude that men's life expectancy has increased. A negative change would indicate a decrease. This is the overall change, but not the increase per year. To decide if a change of 11.5 years is impressive or not, we need to consider the amount of time it took for this change to occur. If life expectancy increased by 11.5 years in a decade, that would be impressive. If it increased 11.5 years in a century, that's still good, but not as impressive. In addition to considering the change in life expectancy, we need to also consider how long it took for this change to occur, which means we need to consider the change in time. 65.6 years was the life expectancy in 1950. 77.1 was the life expectancy in 2020. We subtract to measure change. 2020 minus 1950 is 70 years. Thus, it took a change of 70 birth years for men's life expectancy to increase by 11.5 years. To find the change in life expectancy per birth year, we will divide these two changes. Change in life expectancy divided by change in birth year. 11.5. Life expectancy years divided by 70 birth years equals 0.16428571428. It's a run-on decimal. The directions in the problems will tell you how much to round the answer. In this case, we are asked to round to the nearest hundredth, so our final answer is 0.16. This means that, on average, the life expectancy of men increased by 0.16 of a year for each subsequent year of birth, starting from 1950. Let's answer one more question. Estimate the life expectancy of a man born in 2030. By finding the change in life expectancy per birth year, we can use this information to make a prediction about future life expectancy by assuming that life expectancy will continue to change at the same rate, 0.16 for each subsequent year of birth. A man born in 2020 has a life expectancy of 77.1 years. 2030 is 10 years later. Assuming that life expectancy continues to change by 0.16 per year, means that it will continue to go up by 0.16 each year for those 10 years. We could add 0.16 to 77.110 times, once for 2021, again for 2022, again for 2023, etc. However, instead of adding the same number to itself 10 times in a row, we have a shortcut for that called multiplication. 0.16 added to itself 10 times is just 0.16 times 10, which is 1.6. Adding this to the life expectancy in 2020 will give us a prediction for the life expectancy of men born in 2030. 77.1 plus 1.6 equals 78.7. Thus, we predict that the life expectancy for men born in 2030 will be 78.7 years of age.